Okay, good afternoon, everyone. In this talk, I want to introduce some projection-based analysis techniques for handling high-dimensional data. So this will include some dimensionality reduction techniques, which you can apply to reduce the dimensionality of your data and look for patterns that exist on these reduced dimensions. And subspace clustering, which helps you to identify patterns that exist in different subset of dimensions in your data. And also, I want to discuss some possibility of integrating interactive visualization to help improve the efficiency and the effectiveness of your analysis. So hopefully, by the end of this talk, you will gain some basic understanding of projection-based analysis, some of these most widely used algorithms, as well as thinking about what kind of interaction and visualization techniques you can integrate to your data analysis software to help you get better results. So as Ross mentioned yesterday, when we facing high-dimensional data or multidimensional data, we have the curse of dimensionality problem. So basically...
Sorry to interrupt again. Could I ask you to wear the microphone? Those at the back. Make your talk as difficult as possible. Huh?
Okay. Is it now fine? Okay. So basically, with increasing dimensionality of data, the analysis becomes more and more difficult due to many reasons. One of the main reasons is the distance measure becomes less and less meaningful in high dimensions. This is also related to the problem when Ross mentioned yesterday about the sparsity of data. So when the volume of the space increases very fast, the available data quickly becomes sparse, and all objects often appear to be dissimilar in many ways, which makes it difficult to analyze the similarity between objects in your data. So here's a simple example. So suppose you have a table of your customers recording their hobbies. So here we have 10 hobbies and we have 3 customers. And when a customer has a particular hobby, we mark it as 1, and if not, we mark it as 0. So naturally, when we try to analyze such data, we want to find out the similarity between our customers based on their hobbies. So in this case, we will think probably 2 customers who share some common hobbies, they are more similar to each other than customers who don't share hobbies at all. So in this case, we will say Ada is closer to Cassie than Bob, because Ada and Cassie, they share a common interest, but Ada and Bob, they don't share any interest at all, common hobby at all. However, if we apply some standard distance measure, we may end up with a different story, because if, for example, if you apply Euclidean distance on this data set, the result will tell you actually the distance between all pairwise customers are exactly the same. So this is already a simplified version of data. In reality, you have long unified meanings of attributes in most of the cases. So this is one of the major problems with high-dimensional data. Another problem with high-dimensional data is the subspace clustering problem. So basically, when you have data with high dimensionality, often interesting patterns exist in different subsets of dimensions. So here's an example. Suppose you have a large database of people recording different attributes of individuals, ranging from their eating habit to their sportive activity to their music preference and so on. So actually these attributes will be based on different concepts. And when you have different analysis tasks that are related to different concepts, some of these attributes will be irrelevant, and only a subset of these attributes will be relevant to your analysis task. For example, if your analysis task is based on the concept of health status, maybe only a subset of attributes such as average consumption of fruit or average sportive activity and so on, they are related to your analysis problem. And if you project your data based on this subset of attributes, you may find distinctive patterns easily. However, if you use the 4 dimensions, these patterns may be obscured because of this noise introduced by irrelevant attributes in your data. Similarly, if your task is based on the concept of taste of music, you may find a different subset of attributes that are related to your analysis tasks. And in this case, the previous attributes that are relevant now becomes irrelevant. So this is quite difficult to extract, make it difficult to extract meaningful patterns from the data. So if we want to search for all the possible subspaces to look for patterns, this leads to the problem in exponential growth of the search space. So basically, for every extra dimension you introduce to your data, you double the search space. So to give you a more concrete idea of what does this mean, so I guess many of you have heard about this chessboard problem before. So suppose you want to fill your chessboard with grains of rice. So you start with putting 1 grain of rice on the first unit of your, first unit of your chessboard, 2 to the second, 4 to the third, and so on. Eventually, when you try to fill in all the 64 units of your chessboard with grains of rice, you need a pile of rice that is higher than the highest mountain in the world. And this is equivalent to 1,000 times of the global production of rice in year 2010. So if you reflect this to your subspace search problem, basically, suppose you have a data set of 64 attributes, which is not very uncommon nowadays. If you think about the term vector, the speakers mentioned in the morning, or image data, this is actually not too big data set. However, if you want to search for the subspace, this is exactly the same as you look through each grain of the rice that belongs to a heap of rice that is larger than Mount Everest. So basically, this is computationally prohibitive. The good news is, if you look at the problem the other way around, this also means every time when we remove a dimension from our data, we immediately halved the search space, right? And also, there are some heuristic approaches that we can apply to help improve the search speed. For example, I don't know how many of you are familiar with this a priori principle that is very commonly used for association rule mining. So basically, if you say, I can't find, there's no interesting pattern exists in a subspace defined by variable A and B, or attribute A and B, basically I don't have to look at those supersets of the subspace which contains A and B. So this is the same principle that you can apply to reduce your search space in high-dimensional data analysis. So people come up with this idea of projection. So you can kind of reduce the dimensionality, or you kind of focus on only subset of dimensions in your data to look for interesting patterns. So the essential idea is to simplify the process without much loss of quality. And sometimes when you try to do visual embedding of your data, this allows you to directly visualize the 2 or 3 most important features in your data. So the goal is to discover hidden factors that explain the data and reduce the dimensionality. So when we talk about data reduction, we can go to 2 directions. The first direction is to reduce the number of objects in your data. This is often achieved by techniques such as clustering and sampling. And another direction is projection. This is what we are focusing on during this talk, when we try to reduce a high-dimensional data to a data set with lower dimensionality. And sometimes these 2 directions goes in parallel. So when you have really large data set, you just go on both directions. So In this talk, I will focus on two of the most commonly used techniques, including dimensionality reduction and subspace clustering methods that helps you to handle high-dimensional data. Dimensionality reduction takes two different approaches, sometimes combined together. The first approach is feature selection, when you try to compute or identify an optimal subset of predictive features measured in the original data. And feature transformation creates new features that have more descriptive power and drop less descriptive features. So the first one, you will see a clear example in the PCA algorithm, which I will introduce a little bit in details later. And the second one, there are also many methods that you can apply to do this. However, if you can't be bothered to look into the details, just imagine you have a database of houses recording different attributes of individual house. When you have measurement of all three different dimensions of individual rooms in a house. If you want to analyze this data in terms of figure out what is the relation between this attribute to the sale price of the house, probably it's better to use the area measure of the house, which is the sum of the product of these three different dimensions in individual rooms, instead of using this individual measurement. So this reduces the dimensionality of your data, and the area gives you more descriptive power of your data. So this is one of the examples that you can use to do your feature transformation. The idea of subspace clustering is to project the data to a different subset of dimensions and look for interesting patterns there. So I will give some example algorithms of both approach a bit later. So when we say projection-based analysis, the main idea and the common things between subspace clustering and dimensionality reduction is both of them try to project the high-dimensional data to a lower-dimensional space to show how objects in the data relate to each other. So we want that projection to map the data in such a way that similar objects are close to each other and dissimilar ones are far apart. So this way we can find out, easily identify some patterns such as grouping or outliers in the data. So of course, when we say from high dimensional data to a lower dimensional data, this can be many things. So for instance, if you have a data of 100 dimensions, you can just reduce it to, say, 50 dimensions or 10 dimensions, where you still have quite high dimensionality of your data, but this is helping you to reduce the dimensionality of the data. But in terms of visualization, we're often talking about dimensionality reduction as a way of generate 2D or 3D scatter plot of high-dimensional data. This is when we try to project high-dimensional data to a visual display to show the relations in data. And in terms of subspace clustering, we try to project high-dimensional data to different subset of dimensions to highlight the patterns and outliers. So here's an example of a high-dimensional data projection. So this is one of the part of this benchmark data set of handwritten digit. So each digit, handwritten digit, is encoded by 64-dimensional attribute. And if we project this data to a 2D display, you may end up with such a visualization. So ideally, all the zeros, they're written very similarly. They should stay together. All the ones, they need to stay together. And zeros and ones and fours, probably they're closer because they all have these straight strikes and so on. So this is an example that you can see actually a projection-based analysis can help you to identify some part of similarity or distance between the data, the structure of the data. Although most of these algorithms are based on heuristic approaches, so you can't expect 100 correct projection. I mean, that is probably quite hard to achieve. So given that now we know we have algorithms to help us to do dimensionality reduction and subspace clustering, we still have further challenges. So as many of the speakers mentioned before, this computation is usually quite expensive. And most of these algorithms have complicated parameter settings. It is hard for long data mining experts to understand some of these parameters, as well as how did this algorithm work, and all these multi-step algorithms, what do they exactly do? And this also leads to the problem of interpreting the data mining result. So often people, when they have the data, they don't know the data mining techniques. They have to go to a data mining and expert to ask their help. And this iteration is very inefficient, because the data mining expert will show you the result, and then you will tell them whether this is something you want to see or not. So this is very inefficient. So to improve the efficiency, one of the solutions is integrating interactive visualization. So by interactive visualization, actually you allow the human analyst to play around with not just the data, but also the data mining algorithms, as well as the data mining result iteratively. So this way you can integrate human domain knowledge and utilize human analytical capability, as well as engaging human perception power while you're showing them the visualization result of either your data or the data mining result. So as I said in this talk, I try to cover these two types of projection-based analysis techniques, but also I want to discuss the possibility of integrating interactive visualizations to this analysis process. And I will introduce some of my past projects as constants when we try to develop some visual interface or visualization for these different types of analysis. So I will start with dimensionality reduction. I will only briefly mention the main concept of these two mostly wide-used dimension reduction techniques, namely PCA and MDAs. I don't want to be too repetitive, so I will just give you a brief idea of what these algorithms do. Actually, the easiest way of doing dimensionality reduction is to do manual removal. So if you know your data and you know your analysis tasks, you can easily just filter out those dimensions that are not relevant to your analysis. This sounds very simple, but actually it works quite well. Also, there's some automatic machine learning algorithms that you can apply when you don't have this manual knowledge or human knowledge about your data. So in this talk, I will focus on these automatic algorithms. So I will start with multidimensional scaling because it's quite intuitive. So basically, multidimensional scaling is based on a distance measure which satisfies these following 4 criteria, including it can't be a negative number, and a distance between an object to itself is 0, and it's symmetric, which means distance between I to j is exactly the same to j to I, and triangle inequality, which means distance from I to j is smaller than or equal to distance from I to k and then k to j. So one of the most commonly used Euclidean distance by multidimensional scaling is Euclidean distance. However, there are some algorithms that apply different distance measures, but I'm not going to talk about this during this talk. So basically what multidimensional scaling does is to, given a data matrix that has m attributes and n data objects or items, you first compute the distance matrix between pairwise items in your data, ending up with a triangle-like matrix like this. And given this distance matrix, we will run the algorithm to generate XY coordinates. This I'm talking about visual embedding in 2D, but it can easily be XYZ for 3D and more when you have higher dimensions. So I will focus on this visual embedding part. So basically, you want to generate these XY coordinates for each item in your data in such a way that the distance, the Euclidean distance between pairwise items in the projection space best approximate the distance in the real data space. So as you can easily imagine, this is an optimization problem. So you give a distance matrix like this, you try to find a vector I that in this new vector, the distance between two objects is very close to the original distance in the data space. So I'm not going to talk about what kind of technique you're going to apply for this optimization, but as you can imagine, there's a real need of optimizing this process because the parameter space is really big. Given 150 data points in the Irish data, the parameter space is 300. So when you try to project it to 2D space, so you have to take some heuristic optimization to run the algorithm. So now let's move to the second dimensionality reduction technique, which is principal component analysis. It is probably the oldest DR technique, and the algorithm, as many speakers mentioned before, is based on two assumptions. The first assumption is the presentation of the data in a lower dimensional space should be obtained by a projection to a linear subspace. So we are only capturing the linear pattern in the data. The second one is the criterion to evaluate the representation of the data in the lower dimensional space is the preservation of the variance. So this is different from algorithms such as projection pathway when you try to preserve the deviation to the normal distribution. So these are just small variations between different algorithms. So basically, you try to find a X in your data that maximize the variance on this X as much as possible for the first principal component. So what does this algorithm do is it takes a matrix of n objects by p variables, let's say, which may be correlated, and we summarize it by finding uncorrelated x's, which are also called principal components or principal x's, that are linear combination of the original p variables. So basically, given p dimensions, we generate p principal components. But we sort these p components in such a way that the variance is in a decreasing order. So we can select to which point how many principal components we want to keep at the end. So what does this algorithm aims at? It just imagine you have only 2 dimensions and you want to generate 2 principal components. Basically, you just rotate your axis in such a way that you find the X first principal component that maximize the variance of the data, and then you try to find the orthogonal X in different to this first principle that maximize the variance of the data next to the first principal component. So of course, then you can cut the number of p to a k, which is a smaller dimensionality. This allows you to do dimensionality reduction. So I'm not going to go too much into details, but when I want to just explain a little bit on how to interpret the result of principal component analysis. So often after you run PCA on the software, you will end up with these 2 table-like results. So the first table tells you the eigenvalues of the principal components. Here we say axis. Here we have 10 principal components, and we have the eigenvalues and percentage of covariance and cumulative percentage of covariance. Actually, these kind of give you the same information, but in different ways. So it tells you how much percentage of variance. Probably it's the most easiest way to understand is to look at here and here. So this tells you how much of percentage of variance a particular principal component preserve. And this gives you a cumulative number of the first n principal components. So basically, based on this, you can decide, for example, you want your result to preserve at least 60% variance of your data. You can cut through this point and keep the first 3 components, principal components. If you say, I need to have at least 70, you probably can cut here. So this is kind of something that is helpful for you to decide which, how many components you want to keep. Also, you often see a table like this, where each column represents a principal component, and each row represents an attribute in your data. And these numbers are called loadings. They actually, these numbers tell you how much does this particular attribute contribute to this principal component. So this way, kind of, it halfly interpreted what is the relation between your principal component to your original axis in your data. So at least you need to understand these 2 tables in order to interpret the result. So now we have the, all these algorithms that allows us to do dimensionality reduction, but how do we evaluate the quality of the final projection? So intuitively, we want to look at 2 different types of criteria. So the first one would be how well the structure of the data is preserved. How well are these pairwise distance maintained in the final projection, or how well is the neighborhood between objects preserved in the final projection. And the second one, when we try to look for patterns in the data in our visualization, we want to look at how well are the groups separated. So if you have an overcluttered visualization, you may not be able to find these patterns. So sometimes we have to make a compromise between these 2. So naturally, when you try to tune your algorithm to achieve better group separation, you have to somehow sacrifice the structural preservation of your projection. So there are quite a number of measures that you can apply to assess the structural preservation of your projection, but these are the 2 of my most favorite one. The first one is the stress measure, which is often used for measuring the global structural preservation. So it only detects how well the pairwise similarity is preserved in the final projection. And the second one takes into 2 aspects. The first is the same as this one, pairwise similarity preservation, but the second one is the neighborhood preservation. So imagine you have a 3D ball with objects laying on the 3D ball, and you smash it, or you tear open it. So probably most of the pairwise distance is well preserved. However, the neighborhood is not preserved on this tearing part. So if 2 points are close together and you cut in between, these 2 points will be far apart in your final projection. So this canary measure helps you to identify this kind of problem. So I would prefer to use both when I assess the structural preservation of my projection. And another aspect of the quality of projection is the visual quality in terms of how easy can we identify patterns in the final projection. Again, there are several measures that you can use. The latest one being these 2 measures that we designed in our recent publication. One is this overlapping area measure, which tells you how badly group regions overlap against each other. And another one is overlapping density measure, which tells you how badly objects are plotted in a dense region where these objects belong to different groups. So how can we combine interactive visualization that to help us do the dimensionality reduction and evaluate the result of our final projection? So here we have some general ideas. So as I mentioned before, sometimes you know your data and you know your analysis problem. So in this case, you may want to just easily select the dimensions you want to include in your data or deselect the dimensions you want to exclude. And in some case, you know you can put different weights on the different attributes in your data based on how important they're related to your analysis problem. Also, you can actually display the distribution of your data, especially when you know some information, grouping information in your data. So for example, if you already know there's a subset of objects that belong to the same group, you may want to analyze further and see which dimensions describe this clustering very well, and you may want to enhance the influence of these dimensions and reduce the influence of the other ones. So this can be done via interactive dimension selection. Some other idea is you can apply, you can develop some visual graphical user interface to allow the user design different transformation strategy or try different transformation strategy and see if they can improve their projection result or if they can find beta patterns in the final result. So for time reason, I'm not going to go too much into details of this one. So the general idea is when you have high dimensional data, you can develop an interactive system. We'll give you an initial projection and provide an interactive user interface that allows the analyst to interactively select dimensions or design transformation strategy to transform the data and then reproject the data based on the transformed values. And then you can apply different quality metrics to evaluate the quality of your projection until you get a good projection from the data. And this process can be iterative. So probably I don't have too much time to mention this. We did some interesting work in designing feature transformation strategy to help filtering out noise and remove redundant dimensions in the data. So basically the idea is we may be able to guess some irrelevant dimension based on the data distribution in the data. And we can test this by extending this dimension based on some kind of average or mean value, and then check the projection result. And if both the quality, visual quality and structural quality are improved, or at least one of them is improved and the other one is not badly sacrificed, we can use the transformed data for our projection. And for time reason, actually the result is quite promising. As you can see, the green represent good result and red represent bad result. And we test on different data and using different dimension reduction techniques as well as different quality measures. So as you can see, sometimes we can really increase the visual quality quite substantially without sacrificing too much of the structural preservation. However, it's tricky to design transformation strategy. So sometimes, depending on your analysis tasks, if you want to have better visual quality, you may have to sacrifice the structural preservation. However, this is depending on your how much you can compromise, and you can actually provide a visual interface to allow the user play around different parameter settings until they achieve a very good one. So quickly, I want to move to the second part, which is subspace clustering. Subspace clustering is also called projection clustering. It's relatively new. So most of the algorithms are based on standard clustering algorithms, but they extended to suit the application of subspace searching. So as I mentioned before, in high-dimensional data, often patterns exist in different subsets of attributes, and the dimensionality reduction technique can't identify these patterns because they perform dimensionality reduction over all dimensions. So this leads to the research in developing subspace clustering algorithms. subspace algorithms can be classified into two categories. The first one is top-down approach, and the second one is bottom-up approach. So as the name implies, the top-down approach starts from the full space and look for patterns in reduced subspaces with reduced number of attributes. And the bottom-up one starts from a smaller number of attribute subspace and look for higher super subspaces, let's call it. So basically, the first approach is based on this locality assumption, that is, the subspace of a cluster can be determined by the local neighborhood. And a representative algorithm of top-down approach is this so-called pro-class. The bottom-up approach is quite similar to this association rule mining approach. So when you start from small subspace and increase the number of attributes in your subspace. And the representative one is called clique. So next I'm going to introduce them one by one. So pro-class is the abbreviation of projected clustering. And the basic idea is an extension of K-Madoid algorithm. I don't know how many of you are familiar with K-Madoid. So if not, I first start with the K-means, where you have a data set and you want your algorithm to find K clusters in your data. So what you do is you start from random initialization. So you assign each of your objects with a random cluster label. And then you compute the cluster center based on all the cluster members. So this is the mean of all the cluster members. And once you get this new cluster center, you try to check the distance between each object in your data to individual cluster centers and find the closest one. Then you assign this object to the closest cluster center. You do this iteratively until the assignment doesn't change any further, or certain criteria is made. For example, you run your algorithm for 1,000 times, or you run it for 2 hours, and so on. The K-Madoid is an extension of K-means. So the only difference is, instead of using cluster mean as cluster center, you use an object that is closest to the cluster mean as the cluster center. And then you compute the distance between based on these cluster Madoids. So these centers are called Madoids. So pro-class is exactly the same as K-Madoid algorithm, except every time when we compute the new cluster Madoid, we also compute a subspace that best describes these Madoids. So you first find the cluster center as these Madoids, and then you compute the based set of attributes that can describe this Madoid. And then when you try to evaluate the distance from individual objects to these cluster centers, you just compute the values. You just include the values that are on these selected dimensions that are used to describe individual cluster center. So the algorithm works in 3 phases. The first phase is to select sets of Madoid candidates. So you just randomly select a number of objects in your data as candidate for the Madoid, for the cluster center. And then you try to improve Madoids and compute dimension sets for each Madoid. That is, you try to compute the subspace that describes each Madoid. Finally, you refine your result by improve the quality of the clustering and reassign, recompute the subspace that defines the final Madoids, as well as reassign the objects to the final clusters. So there are quite a lot of input parameters, but I'm not going to introduce all of them in details. So the 2 main ones are the K, which is the same as K-means or K-Madoid. That's the number of clusters you want to find. And there's also an average number of dimensions that you have to specify to your algorithm. So I'm not going to go through all these details, but let's have a look, think about the strengths and weakness of this algorithm. So basically, as you can see, this algorithm is quite simple and straightforward. So it's based on this traditional K-medoid, so it's simple and straightforward. But it inherits some limitations of K-medoid algorithm or K-means algorithms. For example, it's sensitive to the input parameter K. You have to specify the number of K that you want to have, which is often impossible, to get a good guess. Also, it forces you to have a convex-shaped cluster. So basically, you have to find the distance that is close to a cluster center. You end up with this convex shape. You can't use this to detect arbitrary-shaped cluster in your data. Finally, also, this doesn't allow you to have multiple membership. So every time you compute a cluster center, you assign each object to one cluster. So this algorithm doesn't allow you to have multiple membership. So when we think about this data set, when we talk about you have a people data set, one people may belong to a healthy group, but also he may belong to a group of pop music fan. So in this case, this algorithm doesn't tell you this kind of information. But a good thing I forget to mention is ProClass is very helpful when you try to detect outliers in your data. So basically, in the refinement stage, the algorithm allows you to detect outlier by setting a distance, like a threshold distance. If an object is not close to any of the cluster center, you can say this object is an outlier. So this is quite handy. And you can change the threshold and get in. So now let's look at another algorithm that allows multiple membership and allows you to detect arbitrary shaped subspace clusters. This is a typical bottom-up approach, which is called CLIQ, and CLIQ is the abbreviation of clustering in quest. So the algorithm can be considered as a combination of grid-based and density-based. So forget about all these details. Actually, if I show you a picture, you probably can easily understand. So basically start from 1 dimension to 2 dimension to 3 dimensional subspace. We just try to kind of project the data to a grid where we partition the data values to equally sized bins. So this way we can easily detect this densely collected region in this subspace. And if we find a densely collected region, one or many, in a subspace of 2, we will continue to look at subspace of super subspace of these 2. So you have 3 attributes. You add 1 more attribute and see if you can still find densely collected patterns in this region, and so on. If a lower dimensional subspace doesn't contain anything interesting, then we just skip the whole branch of super nodes. So basically, it's like here when we find there are some interesting regions among these 2 attributes, age and salary, then we will continue. Say here, then we will continue to look at its supernodes. However, if we find 2 attributes that doesn't include any interesting patterns, we can easily skip all these supernodes of these. So this way we can quickly narrow down our search, especially when your data is densely populated in some data value regions. So we have looked at some example algorithms. Now I want to move to some of our recent projects on transforming the data mining result from data space to visual space. So as you already now see, actually what subspace clustering algorithm does is to, given a multidimensional data, you just try to find all these patterns that exist in different subsets of dimensions. So the result of subspace clustering is basically, first of all, a list of groups, each containing many objects in your data. But for each group, you also have to associate it with a subset of dimensions that specify this group. So it is hard for the non-data mining expert to understand this kind of information, especially when the number of clusters is large and the number of dimensions is large. So our research question is here is, how do we transform this kind of visual, this information from data space to visual space that helps the analyst to understand what are these results about and how come these are this result. So basically, we did some work in designing different visualization to help people understand, first of all, the subspaces, that is, this set of dimensions that are used to specify different subspace clusters. So here are two examples. So we use this clock-like visualization to visualize the subspace subspaces. So on this clock-like visualization, each of these strikes represents a dimension that is selected for a subspace, for defining a subspace. And we use the length of this strike to represent the importance of this dimension in terms of how well does it describe this subspace. And we designed the importance measure, which I'm not going to give you more details, but if you're interested, you can go back to the reference. And also, we try to use this size of this inner circle to represent the number of objects that is contained in this cluster. This is sometimes very helpful because, for example, here we have two subspaces. We can see the first subspace has less number of dimensions, and the second subspace has more dimensions. However, the first subspace has more cluster members than the second one. And sometimes when we try to run this subspace clustering, we try to avoid these clusters with a small number of objects. In terms of the individual objects in the data, we used this typical grid-based visualization, pixel-based visualization, where we use colored pixel unit to represent data values. So this may not be too easy to understand, but if I explain it, probably I hope it's better. So here, in this visualization, ignore the first part. This visualization, each row represents an attribute, and each column is a data object. And the color of this each unit represents the data value. The reason why we use grayscale and color scale is to distinguish the dimensions that are selected for a particular cluster or not selected. So the colored ones are the dimensions that are selected for a particular cluster, and gray ones are the ones that are not selected. So as you can see, we use these heavy black lines to separate clusters. So here we have 1, 2, 3, 4, 5, 6, 7, 8 clusters, and each row is a dimension, each column is an object. So this gives us already some brief impression on which dimensions are selected for each cluster and the values in each dimension. And this is the abbreviation of this one. We call this cluster layer. So basically, you bin the data into in different clusters into equally sized bins. This is helpful in some data analysis tasks. For example, when you try to compare the range of data values in different clusters. Also, as many of the speakers mentioned, it's important to have different sorting or filtering mechanism to help people make sense out of the data. So basically, we designed a number of ordering heuristics, including dimension ordering, subspace clustering ordering, record ordering, value ordering. For time reason, I'm not going to discuss all of this in details. However, here we can see actually this is the value ordering result of this one. So this one may not tell you so much, but this one already gives you some information. For example, in this visualization, you can see actually most of the unselected dimensions in individual subspace have quite wide range of data values. Maybe this explains why this attribute is not selected to specify this cluster. So this kind of information are useful to analysts to help them understand the result and why this is the result. So here are all the details of the ordering heuristics we've designed. If you're interested, I can give you the reference. And here is a system overview. Also, I forgot to mention we implemented different types of linking and brushing techniques. So if you highlight one thing in one of these three views, the rest of the part will be highlighted as well. So this is quite standard, but it is very useful when you try to explore the clustering result. So I think I will stop here and leave some time for questions. Thank you very much.